Hello, everyone. Just wanted to say hi and hey, guess what, guys? We are working on our last module of the school year. We're starting that today. That will be the focus of our next 3 weeks. I wanted to let you guys know that the district has stated that they don't want any new assignments to go out to you guys after the 22nd of May, which is a Friday. So basically, what we're going to end up having is two assignments this week, two assignments next week, and then two assignments that last week. So you guys have 6 assignments to go. Make sure that you do not work ahead, again, because the way my reports work, it won't capture your work. So make sure you're only doing these two assignments this week, and this week will be Section 13, Topic 1 and Topic 2. Both of these are the unit circle. We're going to work on part 1 now, but before we do that, we really need to make sure you guys understand trigonometric ratios that you learned in geometry and also special right triangles. So this is going to be a little reviewy, but it's been about a year since you guys saw this stuff, so we really need to pay attention to see how this works. So what we're dealing with here is a right triangle. Okay, the right angle here being right here, and across from it, the side being the hypotenuse. Um, Now, what we really have to pay attention to, and what really gets students, what drives students crazy about trigonometry, which is actually very simple, is the names of the sides and how we pick which ones go where and all that other kind of stuff. It really just drives students absolutely crazy. So a right triangle consists of three sides and three angles. Okay. Um, the 90-degree angle we just kind of ignore. Yeah, it's in every right triangle. It's not super important, just as long as it's there. The other two angles are we call one of them sometimes the X angle, the other one the Y. We're just going to pay attention to one of those right now. Just focus on the X, kind of ignore the Y. For what we're doing right now. Now, these two sides here are called legs, okay? Because this third side over here, this is definitely called the hypotenuse, the longest side of the right triangle. Now, the only words you have to worry about here is adjacent and opposite. Adjacent means next to, and opposite means across from. So if we're talking about this x angle, which one of these sides, A or B, would you say would be next to x? Well, it's definitely not this A side over here. It's way over here. So the adjacent leg to this x angle would be this one right here. Okay. The opposite leg to this x angle would be this one over here. All right. So from this x angle, this is the opposite leg. This side is the adjacent leg because it's the leg that's right next to it. And of course, this side remains the hypotenuse all of the time. Now, if we were to switch to the y angle, that would that would make these two switch, because which leg would be adjacent to the y? Well, not this one. This one is right next to the y. So if we're talking about the y angle, we're going to have to take these two things here. We're going to have to switch them. And we're going to say, all right, now from this y angle, this is the opposite leg. And from this y angle, this is the adjacent leg. This is the leg. This is the side that's right next to the y. And again, the hypotenuse does not change. So it's all really dependent on which angle you're talking about. That's why students have a really hard time with this, okay, is the fact that these things switch around based on which angle you talk about. Now, we're going to focus again on the x angle. We're going to kind of ignore this y. In fact, let me just get rid of it so we don't even have to worry about it. All right, so let's focus on this x angle right here. Now, if we were going to do a sine ratio, all right, a sine ratio, this is the stuff that you kind of just have to memorize. What the sine ratio is it's the opposite leg over the hypotenuse. Okay, and all we're saying here, guys, I want you to pay really close attention to this. As this x angle gets bigger or smaller, all right, so let's pretend like this x angle got smaller. Now, if this x angle got smaller, what would happen is this hypotenuse would drop down a little bit. Okay, so let me just kind of show you that. So instead of going where it goes now, if this x angle got smaller, all right, maybe this hypotenuse would go this way now. Now, I want you to look and see why these are the only two things that matter here. If we were to drop this x angle down, does anything happen to the length of this side? The answer, of course, should be no. It stays exactly like it was before. This x angle, no matter what size it is, big or small, does not affect the length of this side. But what it does affect, if you notice, if we brought this hypotenuse down a little bit, you should recognize that the distance from here, let me mark it with my pen, the distance from here to here, where it used to be, and now the distance from here to here, this distance you should recognize is shorter, okay? So what that means is the hypotenuse got a little bit shorter, okay? Well, what happened to the opposite leg? Well, it used to go from here all the way up to here, and now it only goes from here up to here. That got shorter too. And that's the point of these trig ratios. All the trig ratios are saying is as we adjust the size of this angle, the length of this side compared to the length of this side, they affect each other, where this adjacent leg doesn't get affected at all. All right, and that's how sine ratios work. That's why sine is opposite over hypotenuse. Those are the only two sides that get affected. All right, so let me clear up all of my ink here. All right, now if we go to the cosine ratio, now the cosine is the adjacent leg over the hypotenuse. Okay, so let's take a look at that. All right, so when we're talking about the cosine ratio, let me get rid of this here. Delete. Okay, so that would be these two sides here. Now, I understand as x gets smaller, again, this adjacent leg is not going to change in size. All right, that's not what's going to be happening. But what we're talking about with the adjacent leg is the fact that these two sides here have a relationship together. All right, the length of this side affects the length of this side based on this angle measure. Okay, so and the reason why that is that this side has to maintain 90 degrees. So if this side gets shorter, for this side to maintain 90 degrees, this leg here kind of has to go back in this direction, and that would cause this side here to get a little bit shorter. Okay, so again, if we were to make this angle smaller or bigger, that would make this side here shorter or longer, and that would affect the length of this side here. All right, so that's how the cosine ratio works. And then finally, we've got the tangent ratio, and the tangent ratio is the opposite leg over the adjacent leg. All right. So when you're talking about the tangent of this angle, the two sides that we would look at would be this one and this one. All right. And these are the trig ratios that you should write down. These are the ones that you should kind of memorize. And there's this whole thing that we use. Let me get this out of the way to kind of remind us what they are. The first one, sine equals opposite over hypotenuse. The second one, cosine equals adjacent over hypotenuse. And the third one, tangent equals opposite over adjacent. That's that whole thing that some teachers might call SOHCAHTOA, SOHCAHTOA. That's supposed to be a way to get you to remember these. Some teachers say some of her children are having trouble over algebra. Or some, I had a teacher before that said, kind of ignored the S and the C and the T and just said Oscar has a heap of apples. It just depends on, whatever they call those mnemonics you use to remember which is which. But these are the trig ratios that you need to remember. Now, let's see how those work to find side lengths. I have a trig ratio here, or a trig chart. And I'm going to show you how to use this because it really does help with the calculator. But most of the time we use calculators now. We use trig charts when we have a regular old four function calculator, a standard calculator that doesn't have trig ratios. If I switch this over to scientific, hey, look, I've got trig ratios on here, right? I've got sine, cosine, tangent. I can do stuff like that. But if I have a standard calculator, in order to do trig ratios, I need a trig chart. So let me show you how this works again. All right, back to your, you know, geometry days. So here is a calculator. The first, or sorry, a triangle. The first thing you need is you need to recognize which trig ratio you are using. And it's all about, again, which angles and which sides. So you know which angle we're going to use. We're going to use this angle. It's the only angle that they give us that's not a 90. Remember, we never do the math with the 90. We only pay attention to this one. So here we've got an angle, 33 degrees. And then all you have to ask yourself is, where are these sides? The two sides that are involved in the problem are an x and a 14. Now, where would you consider those sides to be located in relation to this 33? Are they the adjacent leg, the opposite leg, or the hypotenuse? And it's always going to be two of the three. All right. So which two? All right. So, well, adjacent means next to. Which leg, not which side, which leg is adjacent to the 33-degree angle? Well, that's this one. And we don't have anything here. They're not asking us about this, so it's not going to be adjacent. So what is this side over here? Well, this side over here is the opposite leg, all right? And this side over here we know is the hypotenuse, right? Because it's across from the 90. So that means we're doing a problem with opposite leg and hypotenuse. That means this is a sine problem. Again, we just get this from memorizing these, ratios over here. So it's opposite hypotenuse. So it's a sine problem, all right? So we're going to go over here and we're going to say, well, I guess we're doing a sine problem this time. So we're going to write sine, and then we always write down the angle measure, sine 33 degrees, and then we write the ratio. Well, the opposite leg goes on top, so that's going to be an x up here, and then the hypotenuse is 14, that's going to be here. And whenever we do one of these trig problems, our job is to get x by itself, all right? So currently, x is being divided by 14. Guys, what math is the opposite of dividing by? Of course, it's multiplication. So we're going to multiply this side by 14. Now, this is an equation. Guys, here's an equal sign. So if you multiply this side by 14, you got to multiply this side by 14 also. All right, so these will cancel out. And we got 14 times sine 33 degrees equals x. And now all we got to do is we got to find out what this is. This whole sine 33 degrees is nothing more than a number, okay? If we use a trig chart, here's our sine column. Everybody see it? Sine. And we go down to 33 degrees. And this is the number that stands for sine 33, 0.5446. So we could take a regular calculator out, and we could go 14, because that's what the number was, times point, and it was 5446. And it tells us that side is about 7.6 or so, right? That's how long that side is. So let me show you what we're talking about here. We're saying this side over here is about 7.6, which makes sense because the longest side of the triangle should be the hypotenuse. 7.6 is definitely shorter than that. But if we threw it into a scientific calculator, we could do that as well. Let me change this to scientific. All right, and now I could do 14 times sine. Oops, this calculator, the way that you do it is weird. We do 33 sine times, and see that's 0.5446, but just a bunch more other decimals, times 14. And you can see that we got the exact same number, 7.62 or so about 7.6. So that's how that works. You could also throw this into Desmos. I really like the way that Desmos works with this. 14 times, and we go to functions, sine 33. And you get 7.62, whatever. You get the same number that we had before. So you can see that all of this works fine. So one thing that you need to check on if you don't get this answer right here, if you get a completely different answer, I think you get 13 point something or other, check over here in your settings and make sure you're set on degrees. We will be talking about radians next week, but degrees are what we're working with right now. Okay, so that's why you may not get that 7.62 number, 7.6. All right, so that's how a sine problem works, and this is how a cosine problem works as well, as long as the x is up here. All right, now what about when the x is not in the numerator? What do we do? Okay, so let me give you an example of that. Let's see, opposite over adjacent. Well, all of these have the x in the numerator, so we're going to have to change the problem slightly. So let's kind of make up our own problem since I don't have any exactly like that. So why don't we do one where, let me get rid of all this fun stuff here. So let's do this one. This is a cosine problem, but we're going to change this around. Let's pretend like that doesn't have that there. So we're going to put the x right here. Now let's say this side right here is 12. All right. So again, when we first try to decide what kind of problem this is, whether it's a sine problem, a cosine problem, or a tangent problem, it's all about where are the sides compared to the angle measure. The angle measure is right here. The two sides that are involved in this problem are these two. The side that is not involved in this problem is this one. So this over here is the opposite side. And so any of those trig ratios that have opposite leg in it, they're not involved in this problem. And if you look back at this, both sine and tangent have opposite leg in it. So the only one this can be is cosine. That's all it can be. All right. So let's go back to this problem. And the way that you write this problem out is you write the trig ratio you're using, followed by the angle measure, and then you write down your ratio. We know that cosine is equal to adjacent over hypotenuse. So the adjacent leg, again, adjacent means adjacent leg, is 12. And the hypotenuse, again, the side that's across from the right angle, is x. All right. So now we've got to do some math, guys. We've got to get x by itself. So when the x is in the denominator, first thing you have to do is get it out of the denominator. So this is a little bit of a longer process, but it's actually easier. I'll show you a little bit of a shortcut. So the first thing we got to do is get it out of the denominator. So this is 12 divided by x. So how do we get it out of the denominator? We multiply it to get rid of it. So we're going to multiply this side as well. These will cancel out. So now we got x times cosine 37 degrees equals 12. And now over here, remember, this is just a number, right? We're trying to get x by itself. X times some number equals 12. So if we divide this side by cosine 37, because again, cosine 37 is just a number, it will cancel out. But that means we got to divide this side by cosine 37 as well. So we end up with x equals 12 over cosine 37 degrees. And we've got x by itself. That means pick up your calculator, do this math. So we get our calculator out, and I'm going to use Desmos this time because, again, I like how Desmos works better. So we're going to do 12 divided by, I'm going to go to my functions and hit cosine 37, and I get 15.02. That, if I were to round this to the nearest tenth, that would be pretty much 15.0. Okay, so if I go back over here, that means this side over here is about 15.0 units long. And that again makes sense, guys. This side is 12. The hypotenuse should be the longest side of the right triangle. If I get a number that's less than 12, I know I've got a problem here, but 15 is more than 12, so I know I'm okay. All right. Now, I did say I was going to show you a bit of a shortcut on this. And the shortcut basically is, look at where we started. When we started this problem, let me get rid of some of this stuff up here. When we started this problem, we had the x right here and the cosine 37 over here. When we finished this problem, these two switched places. Everybody see that? The x went there, and the cosine 37 went there, and the 12 never moved. And so that's a little bit of a shortcut you can do on these problems. And really the way that works is if we put cosine 37 over 1, that's the same thing as cosine 37. Remember, any number over 1 is itself. And what you basically end up with here is a proportion. Guys, when you have a ratio equaling another ratio, you're allowed to switch, one of the extremes with, you're allowed to, this is called switching the extremes. And that's basically what you did. You're allowed to switch the extremes or you're allowed to switch the means. It doesn't matter. You're allowed to switch them. So we can take this and put it here, take this and put it here, and, it's still equal. So that's kind of what we do. So anytime you have the x on the denominator over here, just switch it over here with this one here, and it's just kind of like a really fast problem to do. Okay. So want to make sure we do a tangent problem as well. Now tangents are easy to see. Tangents are whenever you do not have the hypotenuse involved. And if you notice on both of these down here, you do not have the hypotenuse involved. The hypotenuse is here, it is unmarked. The hypotenuse is here, it is unmarked. So we're going to do this one because here's a decimal, and I might ask some students say, well, Mr. Lenny, this might be a little bit harder with a decimal. No, it's not. So we're going to write down the trig ratio we're using, tan, and we know it's tangent because, again, the hypotenuse is unmarked. It is not part of our problem. We're doing from this angle, this is the opposite leg, and this would be the adjacent leg because this is the leg that is right next to the 29 degrees. So we're going to do tan 29 equals, and remember it's opposite over adjacent. So what is opposite the 29? Well, that's the x. What is adjacent to the 29? Well, that's the 5.4. And so now, again, our job is to get x by itself. So what's happening to the x? It's being divided by 5.4. So how do we get rid of it? We times it by 5.4. That means these will cancel out. So we're left with x equals 5.4 times tan 29. So I'm just going to get my Desmos out. All right. 5.4. Oops. Let me get rid of this one here. All right. 5.4 times, hit my function key, tan, I think it was 29. Hope I'm right there. Yep, tan 29. And I just want you to think about this, logically speaking, guys. Remember in geometry, you learned that the larger this angle is, the bigger the side is across from it. Well, if this is a 29-degree angle, I hope you guys know that this is a 61-degree angle. The side across from a 61-degree angle should be longer than the side across from a 29-degree angle. So we know that this side here has to be less than 5.4. So if you put this in wrong, if you put everything in the wrong spot, it should basically tell you you're wrong by this. It would say this side here is longer than 5.4, but when we calculated it, we got 2.99, which is basically 3. So this side here is about 3.0 or so. All right. So that's how trig ratios work. Now there is one other type of problem that I wanted to show you with trig ratios before we move along, and that's the one where the angle is the thing that's missing. All right. These actually are really easy to do. They work very simply. There's actually less work to do. You guys see all of this algebra we have to do when we do these problems over here, moving things around. When you're looking for the angle, you don't have to do any of that. But let me show you this problem right here. So here we've got the angle measure is unknown, but these two sides are known. You still need to ask yourself the same question as before, all right? Which trig ratio am I using? And again, we just have to look at the relationship of the angle with the two sides that we're working with. So here is the angle, all right? And then we got three sides. We've got the adjacent side, adjacent leg. We've got the opposite leg, and we've got the hypotenuse. And you have to ask yourself, which two are being used? Well, this one had no number on it. So that means we're using opposite and hypotenuse. Again, which trig ratio uses opposite and hypotenuse? And we know that to be sine. Remember, it's the sine ratio equals opposite over hypotenuse. So we're going to write down sine. And then we always follow the trig ratio, always with the angle measure. Well, what's the angle measure this time? It is x. And then we're going to do opposite over hypotenuse. Well, opposite over hypotenuse would be 24 over 29. Now, I'm going to use the trig chart the first time to show you why we do this a little bit backwards on the calculator. All right. So this is a division problem, 24 divided by 29. So I'm going to get my calculator out. 24 divided by 29. And I get this number here. Let's round this to 4 places. 0.8276. All right, this 8 says that 5 go up. So 0.8276. Remember that number, 0.82. All right, now, and we did do the sign ratio. So if I go back to my trig chart and I look in the sign column, I'm looking for the number that's closest as possible to 0.8276. All right. So I'm going down my sign and 0.8276. Oh, guys, look at this, 0.8290. That is very, very close to 0.8276, right? 0.8290. So that means that angle is 56 degrees, all right? So what we're saying is this angle right here is around 56 degrees. Now notice it does say round to the nearest degree, and that's kind of a legacy thing. They think you're still using trig charts all day long, and look, there's no decimals over here for angle measures. So even though we can, round side lengths to the nearest tenth, we can only round angles to the nearest degree if we're not using a calculator, all right? Now, how does this work on a calculator, though? All right, well, let me get out my awesome Desmos, all right? And on our Desmos, remember, it was going to be the sine ratio, sine x degrees 24 divided by 29. Well, here's the little bitty thing that we got to change up a little bit. Remember on our trig ratio chart, we went the opposite direction. You have more than one function here. You have sine ratio, but then you have this inverse sine ratio, and this is the one that you would have to use. So you would click this, and then you just type in 24 divided by 29. And there is our 55.85 degrees, or 55.8, or 56 degrees that we just got a second ago by doing this math. So that's how you do angle measures on your Desmos, or on this other calculator. If I use this other calculator here, the way that it works on this calculator, I believe, if I'm not mistaken, I'm going to have to do the 24 divided by the 29 first, and I get a value, and then I hit trig, and I hit second, and it changes it to the inverse sign, and you can see there's my angle measure right there, 56 degrees basically. Okay, and that's when, again, this is in degree mode. When it's in radian mode, we're going to get something else, but we'll talk about radians next week. Right, you got to make sure you're in degree mode. So that's your quick little mini review on trig ratios back from your geometry days. Okay, hopefully that helps you guys. And of course, you can do the same thing here. This is a cosine problem. These two are both tangent problems because the hypotenuse is not involved. Once you start doing these things regularly, you can kind of get really quick at seeing which ratio you're using, how to set it up, and it gets to be really simple for students. Okay. So another awesome thing that we need to remember from geometry is our special right triangles. And I will tell you, students they have so many problems with special right triangles, just like they have problems with trig. When it's an area they really should not have too many problems with. They're actually relatively easy to use. But let's just talk about them really quick. One of the special right triangles, and we're going to use these a lot in the unit circle, by the way, is the 45, 45, 90. All right. This side of the 45, 45, 90, we're going to call S for side. This side over here would be exactly the same. And the reason is there was a rule you learned in geometry that says if two sides of a triangle, or I'm sorry, two angles of the triangle are the same measure, then two sides of the same length, and it's because the opposite, the angles affect the opposite side. When this angle here gets bigger, this side over here gets bigger. When this angle here gets bigger, this side over here gets bigger. So if these two angles are the same, these two sides are the same. Now, how long would this side be in relation to those two? Well, it would be the length of one of those sides times the square root of 2. Why is it the square root of 2? Because it just is. That's the way it is. That's the, the size of it. So if this side over here was, let's say, 6, this side over here would be 6, this side over here would be 6 square root of 2. If this side over here were 8, then this side over here would be 8, and this side over here would be 8 square root of 2. So basically, to go from the the leg to the hypotenuse on a 45, 45, 90 triangle, you're multiplying times the square root of 2. Now, to go the opposite direction, you would divide, and that's actually a little bit more difficult. For instance, if I told you this side over here was, let's say, 8 square root of 2, all right? Well, that's great, all right? So to go from the hypotenuse to the leg, I got to divide by the square root of 2, and that part's easy. You say, Mr. Lennon, you told me this was hard. When I divide it by the square root of 2, and you can see you can cross those out, and you get 8 and 8. And yes, that part really was not that hard to do. But what happens if this side is a whole number, right? What if this side is, let's say, 10, okay? Well, that means to go from the hypotenuse to the leg, we have to divide by square root of 2. And you guys know if you're going to write this in simplest form, you're not allowed to write 10 over the square root of 2. You're not allowed to leave a radical in the denominator, all right? So there's a way that we got rid of this, and I don't know if you remember this from geometry, but you multiply it times this. And the reason why you're multiplying it times this, guys, what number is this? Everybody should know what number this is. This is just a really complicated version of 1. Any number over itself in a fraction is 1. And what does this do? Well, the numerator is now 10 square root of 2. The denominator is the square root of 2 times the square root of 2, which we know is the square root of 4. And the square root of 4 is 2, right? Square root of 4 is 2. And so now the last question you ask yourself is, does this number go into this number, guys? Does 2 go into 10? And the answer is yes. So this side is 5 square root of 2. And how long is the other side? Well, guess what? Same thing. Remember? And that's not even the most difficult way this problem can work. The most difficult way is, what if this number does not go into this number? Well, then you just leave it like it is. All right. So if this number were, let's say, 19, 19, 19, 19, does 2 go into 19? Nope. So this side over here would be 19 square root of 2 over 2. And this side would be 19 square root of 2 over 2. Ugly number? Yes, but hey, it is what it is, right? And then finally, with 30, 60, 90 triangles, all right, if this is the 60-degree angle, this is the 30-degree angle. And the way this works is the side that's across from the 30 we call S. The hypotenuse is twice as long as that, so we call it 2S. And the side across from the 60-degree angle, or opposite the 60-degree angle, is called S square root of 3. So that's the relationship in those side lengths. So, some of those are really easy to do. So for instance, if you were starting here, this is an easy problem. Let's say this is 4. Well, this is 8. It's twice as long. Okay, the hypotenuse of the, shorter, what we call the shorter leg on a 30, 60, 90 triangle is twice as long. And this side would be 4 square root of 3. So that type of problem is easy. If they give you the short leg, it's pretty easy to get the other two. If they give you the hypotenuse, well, that's pretty easy too. Let's say this is 10. Well, that means this is 5, because again, this side has to be twice as long as this side. And that means this side is 5 square root of 3. All right. The only time this gets a little bit difficult, well, there's 2 instances. But the main one you're going to see is, well, if we started over here, let's say this is 7 square root of 3. This is not hard. This is 7 and this is 14, right? But here's where it gets hard is, what about if this side over here is a whole number, all right? So let's say that this side over here is, let's go with 10, okay? Well, that means this side over here is 10 divided by, sorry, 10 divided by the square root of 3. Well, again, how do we get rid of this radical? Well, we do this awesome thing here. We multiply it times another fancy version of 1. Whatever is down here is what we're going to use here. And so 10 times the square root of 3 is 10 square root of 3. And the square root of 3 times the square root of 3, well, we know that's the square root of 9. Guys, what is the square root of 9? It is 3. Does this number go into this number? The answer is nope. So that's how long this side is, 10 square root of 3 over 3. And how long would this side be? Well, it would be twice as long as this side. Well, what's twice as long as 10 square root of 3 over 3? It is 20 square root of 3 over 3. We don't double the 3 because if you double the top of the fraction and the bottom of the fraction, you haven't doubled anything. It's the same exact size, right? 1 over 1 is 1, but if you multiply the top and the bottom by 2, you get 2 over 2, which is still 1. But if you multiply just the top by 2, you get 2 over 1, which is 2, which is twice as much as 1, all right? And you don't multiply, you don't double this because the square root of 6 is not twice as much as the square root of 3. So, basically what we're saying is instead of 10 square roots of 3, we have 20 square roots of 3 now. That's twice as much, all right? Now, the nice thing for us in Algebra 2 is these two special triangles are actually not as hard to deal with as they are in geometry because we have fixed sizes. Remember, you're going to see in the unit circle that the radius is going to be 1 all of the time, and the radius is going to be the hypotenuse all of the time. So just using regular numbers, if this is going to be 1, the hypotenuse of the 45, 45, 90, to go to this side, the legs over here, we're going to divide that by the square root of 2. And again, we're going to do this whole square root of 2 over square root of 2 thing. We get 1 square root of 2 over 2, which is really just the square root of 2 over 2. Now, so in a unit circle that you're going to see in a few minutes, it's always going to be these side lengths. Oops, not this one over here, sorry. We end up with the square root of 2 over 2. So these two numbers here, I know they're the same, but you're going to see them show up an awful lot in the unit circle. Same thing with the 30, 60, 90. The hypotenuse will always be 1. Now, if that's 1, that means this is going to be 1/2 because remember the side across from the 30-degree angle is going to be half the length of the hypotenuse in a 30, 60, 90. And this side over here is always going to be, remember going from here over to here, we're multiplying by the square root of 3, so we get the square root of 3 over 2. So these two numbers here, you're going to see show up in the unit circle an awful lot whenever you do 30, 60, 90 triangles in the unit circle. So first off, we have this thing called the unit circle. Guys, I would absolutely, without a doubt, draw a few of these down in your notes so that you have them. This thing's called a unit circle. It's going to be a major part of the rest of this course. And there's a few things about the unit circle that you need to know. All right. First thing is a unit circle has a radius of 1. You can tell that because from here to here is 1, and from here to here is 1, and from here to here it says it's -1, and that's going to be something else I'm going to show you in just a second, but it has a radius of 1, okay? So really quick, guys, how far is it from here over to here? 1, okay? So it has a radius of 1. Second thing is, it is centered at the origin. This is on a graph, all right? You have to think about this being on graph paper, and this is on a graph, and this is a graph that's just way zoomed in. The center here is at 1, or I'm sorry, the center's at 0, 0, and it's 1 unit out to the right, 1 unit up, 1 unit left, 1 unit down, all right? The third thing is this side here, oops, I guess I didn't put it, this side here is called the terminal side, okay, the terminal side. And the terminal side is the side that's moving. Terminal normally means end. So we're going to, you know, start here, what they call the positive x-axis. We're going to start here, and then we're going to rotate this terminal side either counterclockwise this way, or we're going to rotate it clockwise this way, one or the other. Okay, and then I believe that's everything that I had on this one. I got one more for you with some other stuff. All right, if we rotate in a counterclockwise fashion, we're going to call that a positive rotation. Okay. If we rotate in a clockwise direction, we're going to call that negative. And then finally, the last thing is when we go off to, horizontally this way, we're going X, this is X units because remember this is on a graph. When we go up and down, it's Y units. And if we went X units to the right and then Y units up, this point that we hit right here is going to be X comma Y. So if we went, for instance, 0.3 this way and then 0.6 this way, this point right here would be 0.3, 0.6. Okay. Now, of course, the signs would change depending on which direction we went. For instance, if our terminal side went this way, let's say down here, this would be, our X would be positive because we're moving to the right, but our Y would be negative because we're moving down. Where if our terminal side was over here, for instance, all right, over here on this side, well, that would be negative X and a positive Y. Okay. Oh, there's one other thing I forgot to tell you. This little symbol here in the middle, it's called theta. All right. It's a Greek letter in the alphabet. All right. It looks like a O with a little dash through it. It's called theta. All right. That's the symbol that we use for this right here. All right. So that should be everything we need. Now it says, what sign, positive or negative, is there for each quadrant? And this requires a little bit of thinking here about how sine and cosine and all those work together. And if you remember quadrants, we're talking about graphs. If you remember quadrants, on a graph, you have your y-axis that goes this way and your x-axis that goes this way, all right, with your origin here in the middle. And we call this quadrant 1, we call this quadrant 2, we call this quadrant 3, we call this quadrant 4. Okay, so what they're asking us is what is the sign for these things in all these different locations? So let's talk about sine first. Okay, now if you remember the sine ratio, we're talking sine theta, so sine of this angle. The sine ratio, if you remember, was opposite over hypotenuse. Well, guys, what is opposite the theta right here? Is it the x, the 1, or the y? And hopefully you guys see that the opposite is y. This is opposite. This is way over here, okay? So this would be sine of theta is y over hypotenuse, which is 1. Well, guys, what is y over 1? Well, y over 1 is just y, okay? So when they say sine theta, they mean y, okay? So let's talk about this. If you were in quadrant 1, is y positive or is y negative? Up here, right? It is positive. What about over in quadrant 2? It is still positive, right? Y is positive anytime we're above the x-axis, right? What about in quadrant 3 over here? Well, that means it would be negative. And then what about down here in quadrant 4? It would again be negative. Well, what about cosine, right? Let me switch colors. All right, cosine, the cosine ratio is adjacent over hypotenuse. All right, so here's angle theta. So which of these sides is adjacent? Again, I know it looks like the 1 and the x are both adjacent, but when we say adjacent, we mean adjacent leg, really. So that would be this one, x over hypotenuse. So this would be x over 1. So cosine theta is really just x. All right. So in quadrant 1, guys, is x positive or is x negative? It is positive. What about quadrant 2? Is x positive or negative over here? X is negative over there. What about quadrant 3? Again, anything to the left of the y-axis for x would be a negative value. And then over here, x is going to be positive. And finally, the last one that we're going to do here is we're going to do tangent. Well, remember, tangent is equal to opposite leg over adjacent leg. So over here, if we're going to do tan theta, all right, tan theta. So that really is going to be, so what is opposite of theta? Well, opposite of theta would be this y, and adjacent to this theta, again, not hypotenuse, would be x. So tan theta is y over x. So in quadrant 1, is your y positive or negative? It's positive over, and what is your x over here? Well, it is also positive. Up here, all x's and y's are positive in quadrant 1. So positive over positive is positive. What about in quadrant 2 over here? Well, when we go to the left, y is positive as long as we're up here, but x is negative. So that's really like positive over negative. Guys, what's positive divided by a negative? That is negative. What about down here? This is the weird one. Well, to the left and down, our x is negative and our y is negative. So that's negative over negative, which means that the tan of theta would be positive because negative divided by negative is positive. And then finally over here, our x would be positive because we would be to the right. Our y would be negative. So this would be negative over positive, which is negative. All right. And we're going to need those signs sometimes to figure out where these values could be. You'll see what we're talking about in just a second. We're not quite there, but you'll see what we're talking about. So when you go to do your check your understanding questions for section 13, topic 1, please be very, very careful with one of the questions. It looks like this, and it's one of those where you have to check all the ones that are true. And it almost seems like it's trying to give it away right now because this is going to be one of your answers. But one of the things that you do need to remember a little bit is your Pythagorean theorem. Um, if we wanted to find out how long this side was, for instance, um, if this side is 9 and the hypotenuse is 15, you remember the whole a squared plus b squared equals c squared thing? Well, that means the a is 9 squared plus b squared equals, and the hypotenuse is always the c, 15 squared. So really, I'm going to do this a little bit out of order compared to what you probably saw this in geometry, but we get b squared equals 15 squared minus 9 squared. So if I throw that into a calculator, all right, I'll just use Desmos. All right, 15 squared, 15 squared, oops, minus 9 squared, oops, 15 squared. All right, 15 squared minus 9 squared is 144. Well, that means that b squared equals 144. So if I take the square root of both sides, I find out that b equals 12. Now that means this side here is 12, okay? Now, if we were to reduce all these, right, what number goes into 9, 12, and 15? And the answer is 3. 3 goes into 9 3 times, all right? 3 goes into 12 4 times, and 3 goes into 15 5 times. So when they say cosine of A is 3 over 5, yeah, the reason why they're saying that, remember, cosine is adjacent over hypotenuse, adjacent over hypotenuse. So when they do, this is the adjacent leg, this is the hypotenuse, so they do cosine of A equals 9 over 15, and then all they're doing is reducing that. 3 goes into both of those, and you get this 3 over 5 thing, right? But that also means some other things. For instance, if I was to do sine of A, okay? Well, sine of A, remember, is opposite over hypotenuse, right? So what's opposite the A? Well, that's the 12. What's the hypotenuse? That's 15. So think about what that would reduce to, and that might be one of your answers also. And the same thing with tangent. Think about, remember, tangent is opposite over adjacent. Okay, so keep that in mind as you're doing those, guys, that they may not be telling you everything, but this should be enough information for you to do the first set of check your understanding questions. Now, luckily, the second part of this, guys, is very, very, very fast. I think there's only 3 or 4 slides, plus we've already done all the review work from geometry, so we don't have to think about that. But it says, find the coordinates of the point of intersection of the unit circle and a 30-degree angle. Now, what they're asking us to do, it says find the coordinates. All right, so somewhere on this unit circle, somewhere out here on this unit circle, there's a point that a 30-degree angle will intersect with, and they're asking us what are the coordinates of that point. All right, now um, this is actually not that bad. There's a few things that they do tell us. Since they said this is a 30-degree angle, that means this is a counterclockwise rotation. Remember, we always start from the positive x-axis. In other words, we always start here. Now, if we were to rotate 30 degrees counterclockwise, that would be in this direction, right? Well, I hope you guys know that right here in the middle would be 45, right? So that means it would be a little bit less than that. So something like this, okay? So let me get rid of this and I'll use a line tool so it's a little bit nicer. So what we're talking about is we're talking about coming, let me use red. Okay, so we're starting here. Oops. Hello. Line tool. Okay. It's being a turd right now for some reason. Okay. So we're starting here. We're going out about, let's say, 30 degrees. I'd say it's about maybe right here or so. Okay. So that's saying that our angle theta is a 30-degree angle, right? And what we're trying to find is we're trying to find what are the coordinates of this point right here. Well, what we want to do is we want to drop down using our line tool, I guess. We want to drop a side straight down so that we can make a right triangle out of this. Okay. Oops. Straight down. Okay. So here's our right triangle right here. So if we want to know what the coordinates are right here, we need to know what this x is and what this y is. Okay. And that's actually really simple to do because this terminal side will always be length 1, always. Okay. So, that's really pretty easy for us to remember. And then we just have to work off of this being a 30, 60, 90 triangle. Now, if you remember correctly, when we have a 30, 60, 90 triangle, let me go ahead and bring up a triangle here really quick. This one. All right. Let me orient this triangle exactly the same as this one is. You can see what we're looking at. Flip left, right. Okay. So this triangle here is basically being this triangle right here. So if we have this side length here is 1, okay, and this is our 30-degree angle right here, that means this is our 60-degree angle. Now, if our hypotenuse is 1, we know that the side across from the 30-degree angle, that's the side we call the shorter leg, that is always half the length of the hypotenuse. So if this side is 1, this side is 1/2, okay? And that gives us part of our answer. Remember, when we go x to the right and then y up, this coordinate right here will be xy. So that means this right here being 1/2 tells us that this value right here is 1/2. And we know it's positive because it's going up. Y is always positive when it goes up. Now, what about this side over here? Right? We know that this side here, what we call the longer leg, the side across from the 60, is always going to be the shorter leg side times the square root of 3. So this is 1/2 the square root of 3. Now, we don't really write it this way because this is kind of ugly. So another way to write 1/2 times the square root of 3, I mean, just think about it, 1/2 times the square root of 3. If you were multiplying a fraction times a number, you normally do this, and then you multiply straight across, and we get the square root of 3 over 2, and this is the better way to write this. So this length right here is the square root of 3 over 2, or 1/2 of the square root of 3, and that's what this is right here. And that is what our answer is. Our answer is the square root of 3 over 2, comma, 1/2. That is the coordinate of this point right here. It's the intersection of the unit circle and a 30-degree angle right there. Okay? Moving on to the next one. Find the coordinates of the point of intersection of the unit circle and a negative 60-degree angle. Guys, this negative right here, this negative tells us that this is a counterclockwise, a clockwise rotation. Counterclockwise is positive, clockwise is negative. So we're going to start here, and then our terminal side is going to swing down from here a certain amount. And again, let me go ahead and get a line segment tool. So we're going to start here on the positive x-axis, and then we're going to swing this down. Now remember, right here in the middle, somewhere around right here is a 45-degree angle. So that means we need to go a little bit further than a 45-degree angle, maybe somewhere like this. Okay, and then we're going to go straight back up to right here so that we can form our right triangle. Okay, so we've got our right triangle. Use blue. All right, so we've got our right triangle right here. This is our 60-degree angle. Again, that's the right here. That's our 60-degree angle. So that's our negative 60-degree rotation because we went clockwise, right, from here down to here. Now that would make this 30 degrees. Now, again, this radius here, you know the distance from here out to the circle is 1. The hypotenuse on these are always going to be 1. The terminal side is always going to be 1. And then these other sides are going to have to work off that. Remember, now again, if this is 1, then that means that this side across from the 30-degree angle is what we call the shorter leg, and it's going to be half the length of this. So this is going to be 1/2. Okay. And then what is that going to make this over here? Well, this over here, this side over here is always going to be this side times this, or times the square root of 3. In other words, 1/2 the square root of 3, which we said a second ago was the square root of 3 over 2. But remember, this time we're going down. So I know the length of this side of the triangle is square root of 3 over 2, but since we went to the right, that means positive. We went down, that means negative. We're going to call this side negative. So the coordinates of this point right here, which is what they're asking us, find the coordinates of the point of the intersection of the unit circle and the negative 60-degree angle. That is going to be 1/2, comma, negative square root of 3 over 2. And that is our answer. Okay. One more time. It says find the coordinates of the point of intersection of the unit circle and a 45-degree angle. Guys, again, are we going to go counterclockwise or are we going to go clockwise if this 45 degrees is positive? All right. So hopefully you guys recognize that we are going to go counterclockwise. All right. So we're going to start our terminal side right here. We are then going to go counterclockwise. All right, 45 degrees, which is like right in the middle. Again, I hope you guys can see that this is a 90-degree angle here, so 45 would be right here through the middle. We're going to drop this straight down. All right, and I'll go ahead and complete our triangle here. So we're talking about this triangle right here. Okay. Now again, this angle right here is going to be 45 degrees. That would make this angle our right angle, and that would make this angle up here also 45 degrees, by the way. All right, and let's think about how this works again with the 45, 45, 90 triangle. Remember, these two legs are the exact same length. This hypotenuse is exactly 1. All right, now remember on a 45, 45, 90 triangle, if we go from the leg to the hypotenuse, we multiply it by the square root of 2. But if we go from the hypotenuse to the leg, we have to divide by the square root of 2. So this is 1 divided by the square root of 2, which, we can't leave it looking like this. So we do this is called rationalizing the denominator. We're making the denominator a rational number. So 1 times the square root of 2 is the square root of 2. And the square root of 2 times the square root of 2 is the square root of 4. And the square root of 4 is 2. So this is the square root of 2 over 2. Well, that's how far it is from here all the way over to here is the square root of 2 over 2. And how far is it from here up to here? Well, remember, 2 angles the same measure means 2 sides the same length. So this is the square root of 2 over 2. And that means this point right here is the square root of 2. Well, I don't even know what my brain was thinking there. All right. That means this point right here is the square root of 2 over 2, comma, the square root of 2 over 2. All right. Now, you can put a 45-degree triangle here, 45, 45, 90 here, or here, or here, or here. And all of the points would be here, let's say here, here, and here. And they would all be the same exact values, except some would be positive, some would be negative. Like down here in this lower left-hand corner, they would both be negative. Over here, the x would be negative, but the y would be positive. Over here, the x would be positive, but the y would be negative. But up here, they're both positive. So basically, the unit circle only consists of 45, 45, 90, and 30, 60, 90 triangles and all of their intersection points. You're going to end up with 3 points here, 3 points here, 3 points here, and 3 points here. We'll get into a little bit more of that in the next module. Okay, or the next section. All right, so finally, one more. It says find the coordinates of the point of intersection of the unit circle in a negative 30-degree angle. All right, negative 30. So again, negative 30. You guys know that means we're going to start here. We're going to work our way down. All right, so let me get my line tool. We're going to start here. And we're going to go down, okay? So because negative 30 means clockwise, so we're going to go down here. Again, this would be 45 down here. So 30 is less than that, somewhere around right here. I'm going to use my line tool and go straight up from there to make a right triangle. And I'll go ahead again and close in our right triangle again this time. So starting here, going out here. So now I got my nice right triangle, okay? My right angle would be right here. This would be a 30-degree angle. All right, this would be a 30-degree angle. Remember, the hypotenuse or the terminal side is 1. All right, that's how long that side is. And again, guys, how long is the side across from the 30-degree angle, what we call the shorter leg, compared to the hypotenuse? Again, it is half as long. So what's half of 1? Well, that is 1/2. This side is 1/2. And then how long is this side here compared to this side here? Remember, when you're going from the shorter leg to the longer leg, in other words, the leg that's across from a 60-degree angle, you always multiply this number times the square root of 3. 1/2 times the square root of 3, we know, is the square root of 3 over 2. You guys see how this is half of the square root of 3? So this is the square root of 3 over 2. And again, now all you have to think about, all right, is which one, if you started from the origin, you went a certain amount to the right, and then you went a certain amount down, what kind of coordinates are you going to have, positive or negative? Well, going to the right, this much, I'm going to have square root of 3 over 2. And then going down from here to here, you guys know I'm going to have negative, oops, what was that? Negative 1/2. Right? And there's our answer right there. That's the coordinates. All right, so the last thing we're going to look at, it says draw a triangle, and then it's got parentheses around S, which means it could be one triangle or more than one triangle in the unit circle below to illustrate an angle that has a value of cosine theta equals negative 3 over 2. All right, now let's think about this again. Cosine theta. If we go back to that chart that we had, where we did all the signs. This one. Cosine theta is x. All right. Remember we said cosine theta is x. And it said had a negative. Now that means that we can only live in quadrant 2 and quadrant 3. So that means we're going to need triangles in quadrant 2 and quadrant 3. So if we go back to this right here. Da, 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 da. All right. So this is a negative. So we know we're going to have, this is quadrant 1. Quadrant 2 is over here. Quadrant 3 and quadrant 4. So we're only going to be in here and in here. All right. So we know we're going to draw triangles over here. Now, for it to be negative square root of 3 over 2, now we have to decide, what kind of angle are we going to have on that. Now, I want you to think about how that works. First off, square root of 3 is a very good hint to us. It knows that we are not going to do this whole 45-degree angle thing to right here because that uses the square root of 2. So it's either going to be up to here or it's going to be over to here. One of those two. All right, so let's think about how that would work if we actually did this. So first off, let's try this one and let's see if it works. All right, so let me use a line tool. So if we were to do it to this one, all right, now if we were to do that to this one, that means we would have to close off the triangle this way. All right, and so what that would end up having us do is that would have us have a 30-degree angle here. And that would have us do a 60, or this is our 90 and a 60-degree angle here. And this would be 1. And what we would end up having over here, if you think about that, this would be 1/2. Remember, cosine theta is x. Well, this is not this. Everybody see that? So that's definitely not the way that it's going to go because that's going to give us an x or a cosine theta of negative 1/2 because we are going to the left. This is going to the left. But it's not going to be this one. So that's actually not the right way to do this one right here. So what we need to do is we need to take this one here and we're going to run it over to here. Okay. And by running it over to there, what we're going to do is we're going to take this bad boy and move it to right there. And we're going to move this one over to here like this. Okay. And now we've got our 30-degree angle right here, which makes this our 90, which makes this our 60. And if this is 1, remember this terminal side / hypotenuse is always 1. And that means this over here would be 1/2. And that's fine because this is our y. Remember, this is going up and down. This is our y. But again, if this is 1/2, how long is it from here over to there? Well, remember to go from the shorter leg, the side that's across from the 30-degree angle, to the longer leg, the side that's across from the 60, we multiply whatever value is here times the square root of 3. Well, what is 1/2 times the square root of 3? Okay. And we said that that is the square root of 3 over 2. And why is it negative? Well, because we're going to the left. All right, we're starting at the origin, we're going this way. So this is negative square root of 3 over 2. So this is one of our triangles. This is, this one, it doesn't say find the coordinates. It says draw triangles. So this is one of our triangles, okay? So let me undo that up. All right, so this is one of our triangles. Now the other triangle that we're going to do, what other triangle would have the exact same cosine theta? In other words, the exact same x? Well, the only other one would be a matching triangle right down here. So that triangle would go from here over to here, and then it would go right back up here, and it would match up with this one. And so what we would end up with is two of pretty much the exact same triangle. Again, this one here would have a 30-degree angle here, a 60-degree angle here, a 90-degree angle here, a terminal side of 1 or a hypotenuse. This side here would also be 1/2, although this time it's negative because it's going down. But both times, these both would have negative square root of 3 over 2 as these side lengths here, as these x's. And that is our answer for that. Okay. And finally, now you can do your check your understanding questions for section 13, topic 2, unit circle part 2. These are the only 2 assignments you have this week. You do not have a third one. Next week, we're also going to have 2 more. And the final week, we're going to have 2 more. And that will be your last assignment for, your last assignments for this particular school year and quarter, because the district has said that they don't want us to send out any new assignments for students after May 22nd. So that leaves us, these 3 weeks to handle these. We're not going to get done with 100% of what we're supposed to get done with, but we're going to get, you know, as close as possible. Okay, guys, have yourself a great week. And just try your best on those questions, and I will see you later.